Okay, what did we talk about on Wednesday? What's the keyword that we just added to our arsenal? Yeah, const expression. Thank you. Cool. Const expression. What does const expression do for us? Or what is it themed around? Yeah, compile time. It is the idea of moving your code into compile time. And, okay. Nice, okay. So we had this example. Was it this example? Or was it a different example? Oh, you know what? Okay, just one sec. Where is it? Here we go. Okay, so we had this example, right? Okay, what did this do? Let it re-enter your brain. Okay. What is this maximum prime differences function supposed to do? Anyone remember? Yes. Exactly, yeah. So the point of this function is it finds the maximum distance between any two primes. And so the algorithm, yeah, is it starts from the left-hand side, then it starts from the right-hand side, and it finds just like the first primes on either side, then calculates the width in between them, right? But kind of just like looking at this, it's pretty clear what the answer should be. Like if we just look at this, like we can see like, okay, so there's a prime number right there, and there's a prime number right there. So let me zoom in a hair. So if I just like look at this, it looks like the answer would probably be 3, because it's like 1 hop, 2 hops, 3 hops. So 3 would probably be the result returned by this, just by looking at this. Like I don't even need to run this code in order to know that the answer is going to be 3. Okay? So therefore, when we specifically add this like const eval and const expression qualifier right here, what does that do to our generated binary? Okay, tell the person next to you, what does that do to our compiled binary? Let me pull up the assembly file in about 10 seconds and we'll look at it. Oh, also, does anyone remember how to generate assembly code from .cpp code? What is the flag for C++ compilers? Yes. Yeah, -s. Cool, okay, so -s, good. And then we still do -o for output. And then, yeah, it would be like main, oops, come on, main.s. Okay, so I just now generated that. I meant to do G++, bad. Okay, and what's going on here? Maybe I need to specify C. Oh, you know what? Actually, I'm going to use make instead, because I think in my make file, I actually specify, I specify a few extra parameters just to simplify the output of the assembly. So I'll release this code today, and you're welcome to play around with it more. But okay, so let me just run make main.s instead. Okay, so there we go. So I've now generated this file, and now when I look at this, of course, you were all screaming to the person sitting next to you. You were saying, so in main now, okay, so we still have, hold on. This is not right. Okay, sorry, let me pull this up. Okay, so if I pull up main.cpp, here's the main.s that I just generated. And if we look at main, what does main have? It's very simple, right? What is the only thing that is inside of main? Yes? Yes? So it's actually not even printing anything, because all we're doing is just returning this value, which is 3. So it's just returning the constant 3. Yeah, super cool. And that's because of this const eval and const expression. So if we like got rid of these right here, and now did make main.s, and I think I just have to refresh that. Yes, so now if I look at main now, okay, so by removing those keywords, now you can see that my binary is now way larger. It's doing all these function calls, it's calling all of this and things, which is maybe necessary, maybe not necessary. But that's like just kind of just brushing upon the surface of how powerful the C++ compiler is expected to be, whether it's Clang or Visual Studio or G++. The C++ compilers are extremely powerful. Okay, so today I wanted to explore even more and look at the keywords auto and template. Okay, so let me pull up the first example. I did not cover auto as in depth. Yeah, so I want to cover auto a little bit more in depth today. Okay. Resetting a couple things. Okay, good. Okay, so here I have basic main.cpp, so I can print something. What argument does this function take in? What type of argument is taken? Okay, just shout it out. Integer, thank you. Okay, yes, string. No, integer, so okay. Now if I go in, compile this and run this, what will the output be? You can just shout it out. That is what I am expecting too. I'm expecting it to be 1, okay? Good, so I just compiled it, and it's now running print on 1. There we go, exciting, okay. Cool. So we'll revisit this, but really quick, so let's quickly review what we already know about auto. So if I wanted to create, I don't know, maybe an integer, right? So I might go like int x equals 0 or something. If I want, I could just replace this type name with the keyword auto. What auto will do is it will automatically figure out whatever type you were trying to make, and it will now insert the correct type for you. So if I wanted instead, I could call this x1 and give this value of 2. And if I now hover over auto, and it's taking a second, there we go. You can see what type does that say? Yeah, it's an int. And it's an int because I've specified it right here to be 2. If I want, I could also do auto, I don't know, hello is equal to hi. Okay, good. So if I hover over this, what do you think this will be? No? Maybe a string. Okay, let me check. Okay, const char star. Okay, cool. So maybe that's what we wanted. Maybe we did want a string. Does anyone have an idea of how we could make auto be deduced as a string, like an std string instead of a const char star? How could we make this now decide that this is a string? Okay. Okay. Yeah. Yeah, exactly. So I'm thinking that we can just call the string constructor. So we can just do std string, save this, and I guess I have vector. It's probably fine. Yep, there we go. So now when I go and hover over hello, then now we can see std string. Okay, so auto, kind of does its best to find a type that will work in your situation, but sometimes it's not actually the best. Sometimes, well, what if we didn't want an integer, but maybe we wanted an unsigned integer? We could come in and we could add a u to the end of this to add the integer qualifier or whatever it's called. And now you can see that if I hover over this, now it's an int, an unsigned int. But auto kind of works best when you are grabbing objects, like classes, but not so much for primitives. One of the best use cases for auto is for iterators, because the iterator type is quite complex. So if I had a std vector, okay, and this maybe int v, good, and if I wanted to now create an iterator for this, an iterator meaning you could make a for loop that goes through like all different elements. What you may do if you wanted to like really spell it out, I believe you'd do like std vector, then you'd specify it for int, and then you would now grab the iterator type. And there we go. So now, and then we can call this it, and we can say this is v.begin. Yeah, and after like this really long type name, finally now we have this it, which we are able to go through all the different elements. And this is a perfect example of when to use auto, because now it simplifies out this line and also makes it a little bit more consistent. Yeah, it makes it easier to read. Now there's just less on the screen. Okay, cool. So hopefully this was all kind of a review for auto. I've already, as was said, so I've already talked about auto a bit. But the next thing that I want to show you is maybe something that you have never seen with auto. So here I have this print method up here. Remember, so it takes in an integer. Okay. What would happen if I changed this to auto? Okay. Anyone seen this before? So turns out that this is actually totally fine. So I can compile this. You can see, so I auto x. Here I'm calling print 1 right here. I'll quickly just comment out all this. So if I now go and run this, so we actually get an error because it expects the C++20 standard. So that's fine. So we can just add the C++20 standard as a command line argument. C++20, okay? And now it compiles, and now it prints out 1, okay? Good. If I want, I could now print out something else. So I could go and print out maybe this string hello. There we go. So now it prints out hello, all from this very simple kind of function right here. So we've now made like a generic function that works across basically like any type that we want. Pretty sick. If we want, we could also have it, we could give it a auto like return type. We could say like return x. This is totally fine as well. Okay. Yeah, question.
So when you do the C++20, what is that really doing?
Sure. So you're asking like what does this argument actually like do for us? Yeah. So what G++ does, and what basically all C++ compilers will do, is they will enable or disable certain parts of their like tool. Like they will say, like, yes, I do support having like an auto return type or auto parameter type, but in order for that to be allowed, I want someone to like explicitly say that they want this. And the reason for that is for consistency, because maybe something in the future will be deprecated, and maybe you want to use like a specific version of C++ that uses a uses a feature that like is now deprecated. So like yeah, maybe you want to specify C++ 98 or something, and if you try adding now C++20, then maybe it won't work. Or maybe by enabling C++20 features, maybe it will break things in other ways, because the more up-to-date the version, so if we want, we could also do like C++23. This is the not the most up-to-date C++ version. The most up-to-date is C++26, although it's not supported by this G++ version. Might be supported by G++13. Okay, there we go. Yeah, so G++13 actually supports, not 200. Okay, hold on. Okay, yeah, so C++26 is only provided by like some cutting-edge compilers, not G++13. But the more up-to-date you go, the more likely you're actually going to encounter bugs in the compiler, which is kind of also like a weird thing, because I bet a lot of you kind of just take for granted that your compiler just works all the time, no matter what. Compilers are just, they're software as well. Compilers absolutely have bugs. Me as a chip design guy, all of the Verilog tools, all of the the chip design tools are completely filled with bugs. And so about 50% of the time when my code isn't working, it's actually not my code, it's actually the tool's fault. And so I will often like have to reach out to people and help get their tools fixed. Yeah, another question.
Follow-up. So when we do our CMake
Yeah.
and it makes the make file,
Mm-hmm.
does it look at these and automatically include the flag?
Oh, great question. In CMake, you have to explicitly say what C++ version you want. So here is a basic CMake file, and I actually specify the standard right here. And so I think in all the files, I think I've given you 17, but in your upcoming lab, I will likely give you as starting C++ 20. Yeah, good question. Okay, cool. Okay, so this is auto. However, yeah, this is a C++ 20 feature, but people have actually been able to make universal kind of functions like this for a very long time, at least since C++11, maybe even before that. And what was used more popularly before auto was a concept called a template. So let me give you a quick demonstration of that. It's very similar to what we already have, where what we do is instead of having this auto type, we will, at first, we'll say template, and then we put these brackets right here, and then we specify a type name T. So this is going to be our type now that we pass in as our parameter. And this, that could also be on the same line, but it's often put a line down. And this is exactly equivalent to what we had before with the auto keyword. The only difference is it's just a little bit more verbose. So now if I go and compile this, it doesn't work. What's going on? Thank you. Perfect, good. And I'm also going to go back to C++ 20, just in case there are bugs. Okay. Sure, cool. So there we go. So yeah, you can see, so it's the exact same feature, just a little bit more verbose. But templates actually give us extra functionality and things that are useful. One of the things is that now instead of auto, and instead of just throwing auto everywhere, now we can explicitly, now we have this explicit type right here. So this T right here, this actually represents, the type of this X. Like if we hover over it, you can see that it has this T type. So if maybe we wanted to have like now a vector of T types, now we can do that because you can't have a vector of auto types. Okay. So let's walk through this next example together. So here I have this stack data structure. And so it's stack data structure. So as you would probably imagine, it has push and pop methods. It also has a peek method. And take a look at this. What type of data does this stack store? Okay, so it says here's max size. So this is the number of elements that this stack can have. So what are the elements that are stored inside of the stack? Here's where max size is being used. Yeah, integers. So this is a stack of integers. Yeah, okay. So take a second and look at this. Think through how we could potentially change this to now not be an integer stack, but instead be a template T stack. Okay, cool. Think about that. Question first. Absolutely, yeah, and that is something that we'll talk about in just a little bit. Yeah, putting qualifiers on what types are allowed by certain template implementations. We'll talk about that. Okay, so good. Okay, so hopefully you're kind of looking at this. So maybe the first thing, so this push method. So instead of pushing an integer, okay, we will probably want to push our T type, and for pop. Looks like that doesn't change. But then for peek, we probably want to return instead of an int type, probably another t type. Okay, so that's kind of the sort of generic things that we can do. In order to obtain this this t type, we will need to specify that this is a template. So let's do type name t. Okay, so now that means that this stack must exist now as a template. I'm also going to, let's comment this out for just a second. Let me just show you this example working first. Okay, turn to the person next to you and tell them what the output of this main will be while I go and compile it really quick. All right, is this what you were all imagining? So first, we push a bunch of things onto the stack until it becomes full. Then we pop everything off the stack until it becomes empty. So that is what this main function does. Okay, let's see what happens now when we want to add this, when we want to change this to be a template type. So notice that we now get an error here. And the reason for that is we can't actually have a stack object anymore by itself. Now we need to specify specifically for what type this stack needs to work with. So what we currently have is just an integer. So the way that we specify a template like type is by these brackets, and then you can say int. So there we go. So this will be now, the stack object will now be a stack of integers. And then similarly over here, we can specify that this is also a stack of integers. So now that fixes our code. So now we can do make and dot stack again. It'll work the exact same. But yeah, maybe now instead of int, maybe we want like strings or something. So okay, let's go and modify this to now make it be generic. So okay, what is the first line of code in this that we need to change in order for this to not be a stack of integers, but be a stack of maybe like strings or, some sort of generic type? What is the first change that we need to do? Okay, yeah? Yeah. Yeah.
Where you're accessing the max size member, is there a way to not have to specify the generic type to get it out? It's like, it doesn't change it.
So what is cool and what we'll see more is you can, if maybe instead of max size, maybe we wanted it to be like size of t or something. So the idea is that potentially this max size might be dependent on whatever type we're passing in. And as far as I know, there's not a clear way to know whether this max size const expression value is going to be if it requires a type in order to be calculated. So therefore, it just like always assumes that it needs a type. But yeah, good question. Okay, so first line of code. So here, so instead of storing a list of integers, what do we probably want to store? Not quite. So here's the type name t. So here is what we are saying, like this is like an argument, right? So when we pass in, like when we create a stack object, that's the thing that we're passing in. Like if we want, we could now make a string stack, or maybe a double stack. That's probably going to work a little bit better. So here, if we have a double stack, I'll call this like stack double. Okay. So in order to make stack now work for both when we're passing in an integer type name or a double type name. So this t will elaborate out either to int or double. So instead of an array of integers right here. Instead, we would want to have an array of T-type objects. Okay? Yeah, making sense? Okay, so for push, how would we modify this now in order to push on a generic object? Okay, yes? Okay, so the argument type, yeah, instead of const int, probably it's going to be const t. Okay, good. And then pop, does anything need to change? Don't think so, okay. And then peek, now, so we are returning this object. What is data? What type is data? Well, yeah, it's an array of T objects, perfect, okay. So now when we return it, what do we need to return? Yeah, we need to return a T reference. So there we go. So now we have made this class be generic. Now we are pushing a constant, or a generic type, which can either be an integer, like here, or it could be a double, or maybe it could be a string. There we go. And this all will compile. And if I now compile this, then there we go. And we can see that, yeah, it still runs the integer stack. If we wanted now, we could do the string stack instead. It'd be fun. Okay, let's do that. Let's maybe just, oops. Okay, cool. So just stack string. So this is going to be a stack of strings. And here we are pushing I. What type is I here? Why are we getting this error? What type is I? Yeah, I is an integer, and we cannot put I, I is not a string. So what we would need to do is cast this to a string. What we might be able to do is just do something like, actually, can we do this? Can we say instead of, no, hold on. Let's see. Does this work? std string. I need to just include string. Does this work? Ah, okay. Anyone know how to convert integers to strings? So S2I? Yeah. Two underscore string. Fantastic. Okay, cool, good. So now we are pushing, in theory, all the string objects, and maybe just to make sure that this is correct, we'll put say hello plus. Okay, cool. So if I now run this, stacks. This is how we specify a generic type, so type name T. This is the exact same thing that std vector will do. So if I now create std vector, so notice it's the same thing. So brackets int v, and if I want, I can, let me include vector really quick. Okay, if I now hold control and click on this, then it can actually take me to the implementation of vector. And look at this. So we can see vectors also use template types. And here, this TP, this is the type. Then here, this is allocator. This is unrelated, unimportant. But yeah, but this is vectors still use the exact same thing that we've used for this stack object. Same thing. Can anyone think of other objects that might use templates? Maybe std pair, right? Okay. Yeah. Any other ideas? Yeah. What was that? Unordered maps and maps. Yes. Okay. Anything else? Yeah. Arrays. Absolutely. Yeah. Another one. Yeah. Lists. Sure. Another. It would be smart pointers as well. So almost everything in C++ is built off of templates, and the reason for that is because it helps kind of create things at compile time. Let me go back to the previous example here with this print method, and let's actually look at what the assembly is doing. So if I go back now, so maybe, yes, try to think like what the assembly output would look like for this generic T-type. Like, okay, like if you were the designer of G++ or Clang++, like how would you go and implement templates? Okay, so maybe think about that for a second, and then I will go and compile this but to an assembly file. Okay, -s-o main.s. Okay, so here we can see that I'm calling print twice. Actually, let me quickly, I'll just print it one time really quick. Okay, so here I'm just printing out it as an integer, and I can open this main.s. And okay, so it's kind of a pain to look through this big assembly file, and we won't really look through it, but I at least can search for this function print. Okay, any guesses for how I can search for print in this? How would you try to find like where print is? Like, would you just scroll through it, or what would you do? Okay, yeah? Yeah, okay, so let's Control F for print. Okay, so it looks like there's a bunch of instances of print here. Okay, and actually, oh, is this it? Okay, so this, if you're familiar with assembly, this here represents a label. So actually, yeah, this looks like it is the print method, but and the way I can tell it's a print method is because of this colon right here. So whenever you have this structure where you have like a weird like label, and then you have a colon, this denotes that this is like an address in our program, and it's a function pointer effectively. Like this is a memory address, and like this location of this first instruction is a function pointer. And so what we can do is we can search for this print, but we could use a regex now to not just find any prints, but to find any prints that eventually have a colon at the end of the line. And this will now tell us like how many times we see print. So okay, so if I do now dot star means it'll now match for the entire line. Okay, and then I will do colon. Now we can see that there is only one single instance of this print right here, and here is this call. Okay, so when we go and print out this integer 1, now it looks like this is the function. Watch what happens now when I uncomment this hello right here. So if I now compile this, okay, and I might need to just refresh this. Okay, so now I've refreshed it, and I can search again for print. Okay, notice anything different? So now how many, now how many print functions are there? Okay, now there's 2. Okay, well, what would happen now if I go and say like 1.0? Okay, if I now go and compile this, well, now there are 3 function implementations of this. Okay, so with this demonstration, what does that mean now that template does? Like, is template itself like code that is run, or instead like what is template used for? Okay, yeah. Exactly, yeah. So what template does is instead of like actually treating this as code to run, which would like, it would be way too complicated to figure out all the types, because like if you're trying to print out like a string or an integer or like a random object, it's impossible to know how generic to go. So what will happen is instead a template is just used as a generator. So it will generate for you every function that you need, depending on whatever functions you actually use it for. whatever instances you use it for. So, okay. Sorry. Okay, cool. Yeah, so here we are using it for an integer case. Here we're using it for an std string. And then here we're using it for a double. If I go and do this now, if I call this double function a few times, if I call this for like 2 and 3, then now how many like print implementations do we imagine would happen? Okay, how many of you say 5? Okay, because there's 5 print functions. Okay, how many of you say 3? Okay, yeah, I believe the answer would be 3 because there are only like 3 types that this function needs to account for. So if I now search for print again, there we go. You can still see that there's only 3 print methods. Okay, cool. And I'll just also quickly show you, this is the exact same way that auto functions work as well. Because like I said, auto is basically the exact same thing as template. So if I now go and run this, you will see, oh yeah, I just need to specify C++20. Okay, and that's not very interesting because I haven't changed anything. But if I now go and compile this, you can see that I have just 1 and string. So now we can see that the total number of print like implementations is just now back down to 2. Very cool. Okay. Any questions on this? Feeling okay? Okay. Yeah. C++ compilers. Yeah, very, very powerful. And another thing is this is all done at compile time. So Python will also allow you to do similar things, right? Where you can pass in just like any random value into a function, and it will run the function based off of that object. But what it has is a big, long list of branching instructions that's like, okay, like this object that I've just received, like maybe it's a print method. Yeah, maybe it's Python's print method. What it will do is it will be like, okay, like is this an integer type or is it a float type or something? And it'll have to deduce what that type is at runtime. In C++, the type is determined at compile time always because C++ is a strongly typed language. So all of the functions, like every destination, every bit of code that you write, it is all figured out exactly the branching destinations at compile time. Yeah, question? Mm-hmm. Right. Yeah, so Python, that is why Python is just inherently slower at everything. It's because Python, every single time it ever needs to handle any bit of data, it needs to, at runtime, deduce what type it is and deduce which function, which like bit of code to jump to. But in C++, like you can very clearly see all of the different like implementations of each of them. Like here, like this looks like it is probably the integer print method versus down here, you can see actually like here it's calling this basic string. So here is the string implementation code. Yeah, question?
Are there any ways for Python to get around that?
There are a few optimizations you can do, yes. I don't know them off the top of my head, though. One thing that you can do, you can specify actually types in Python, but I think it's just a suggestion. I don't know if it will actually speed up your code, but you can use types in Python. I think what people will often do when they really need a high-performant bit of Python code is they'll actually just write it in C and then call it from Python. Yeah, I know that's kind of the most popular. Yeah, good question. Was there another question? That answer? Oh, yeah, question. Well, Python, that first call, it will need to check the type and it'll need to figure it out. But then once it's running in like a C environment, then all of the C code will run very speedily, and it won't need to figure out the types, like within the C code. Yeah. Does that answer your question? Okay, sure. Yeah, another question. Oh. You're saying linking C code to Python? That's actually exactly how it works, yeah. So when you want to run C code from Python, you would have to compile your C code as a shared object file, and then you would access your shared object file from your Python. Yeah, we can have a Python day later if anyone's wanting that. Yeah, question?
Let's go back to template.
Uh-huh.
I'm wondering, like, hypothetically, if you wanted a stack object
Yes.
that can hold multiple types,
Would you use template or auto for that? Yeah, great question. Okay, so if you wanted to have a container with a bunch of different types, there are a few ways you can do that. You could use a bunch of template types. The issue with that is if you wanted it to be a dynamic stack, to where like you can add on like a bunch of different things, then you could not really use templates, because remember, templates, the like types must be determined at compile time, but you can't really push like dynamic types like that. How you would implement that, I don't know, any thoughts on how you would implement a container of different types? Any thoughts? It's something that we've already talked about in this class. Okay, yeah. Yeah? Yeah, so we can't use auto for that. And the reason, is auto's types are determined at compile time. So if a user wanted to add things to the stack, that's not something that they would know ahead of time. Yeah, so you can't use auto. Okay, what's the other C++ feature that we've already spent a lot of time on talking about? Okay, yeah? Not a map. Okay, yes? Not enums. Yes? Const reference? No, not const reference. Okay. Think, okay, when have we wanted to have a list of a bunch of different types where each of those types maintain their functionality? Okay, I just, like word for word, gave you the definition of one of our terms that we learned about already. When you have a list of a bunch of different objects that, even though it's like all in one list, they all maintain their existing functionalities. Yes? Polymorphism, yeah. So that is how you would implement an array of a bunch of different object types, is you would probably have a base class that would be base object or something. And maybe that base object, I'm not sure exactly what you would have. Basically, but that's how you would do it. So it was with polymorphism. If you wanted to do it in like an unsafe way, you could also use something called void star, but that's not something that I was planning on talking about in this class. But yeah, you could also use void star. That's what like old school people used to use before polymorphism. Yeah, okay, sure, cool. Okay, there's one more example that I wanted to talk about. So templates go extremely deep, extremely deep. That is what a lot of modern day C++ developers do, is they do 80% of their work in like const expr template world, something called meta programming. And I want to show you a basic example of that. I don't know if we have time to do everything. Actually, we might have time to do everything. Okay, so where is it? Yes, okay, cool. So here I have this basic file, not meta programming yet, meta templates. Okay, so take a second, look at this, turn to the person next to you. What will the output be to console out? Okay, I'm going to compile it. Okay, so let me walk through this, this syntax really quick. So right here, this is what we've already seen before, where you can have a template function, right? We can also have a template class, but in this case, it's a template function, where we are passing in this type name, and so we are printing out any value here. But then we have a couple overridden template values. And what these do is they say, if someone comes along and maybe they want to use a double instead of just like, or if they want to specifically use a double instead of just like any random generic type, they're specifically looking for a double, then now please use this implementation. So what this implementation does is it just sets a certain number of decimal points to be drawn. Similarly, down here, we say if the type is a string that they are passing in, then go and put these quotes around it. So that is what, that is another really cool part about templates, is you can specify the behavior for specific types. So here we can say that we're overloading it for doubles. Here we're overloading it for strings. So I can now compile this and run it. Okay, there we go. So we can see it's first printing out this integer. It's just using the general default case. Then after that, it's printing out 3.1 using the double case. And so it's printing out, looks like 8 decimal points. And then it prints out hello, but it uses these quotes right here. Okay, absorb this for a second. What if we now wanted to get this working with maybe a vector of integers? Okay, think about that and tell the person next to you, what is the code that we could add to now get this working for a vector of integers? So I'll go and print this out. Okay, so we'd probably start with our existing override template. So let me come in here and just copy the string value. And so maybe instead of a string, what type would we put in here instead? Yeah, vector of ints. Okay, good. So let's just see what happens. So, okay, good. Is this gonna? Oh, are we okay? Print, no instance. It's a weird error. Okay. Thank you so much. Okay, perfect, awesome. We get another error, though. Let me get rid of this. Also call this a V instead. Okay. Okay, so what is the issue now? So if I hover over these squiggles, has anyone ever tried to print out a vector like this before? Okay, what happens when you try to print out a vector like this? Yeah? Right, so this will just not let you. It'll say like vector does not have this function, therefore it will kind of freak out. So what we need to do is instead of printing out the vector itself, instead we need to do what to this? Okay, yeah? We could. I would say, yeah, okay, what could we do if we didn't want to override the operator and we just wanted to print it out? Yeah, exactly. Iterate through it. So let's go and do that. So we can say for, say auto, say const auto. That probably makes more sense because it's a constant thing. We can say for each object v inside of, each object x inside of v, and we can print out each object x. We'll also print out maybe a space. Okay, and then finally we can print out a new line at the end. Okay, there we go. So let's see if this works. Okay, cool. Is this what we expected? Good stuff. Okay, now let's say your boss comes up to you and they're like, oh, we're loving this new print feature. Our customers love this. Could you now go and add support for not just vector of ints, but could you just do it for vector of every single object ever, and maybe also have it work for arrays and any sort of iterable object? Okay, thank you. You have 10 minutes to do that. Okay, what would you do? Would you just be like, okay, cool, so vector of that, and then you just start copying it? It's like, okay, let's do it for vector of doubles now. Okay, this one will be for vector of strings. Okay, this one will be for vector of polygons. It's like, okay, this one will be, would you want to do that? Or what would potentially another solution be? Okay, yeah? Yeah, so I think there's some cool features that we can do. So I want to show you the solution. And this is where things go from all right, this is fun, Ethan, but okay, it's not that hard, to looking at C++ and being like, oh my God, that's still C++? So hold on to your boots. Okay, you ready for this? So here we have this main function down here. I'll get rid of this. Okay, and we have this this vector v. Okay, and when I now try calling print on v, then this will work. But it will work even if it's an integer or double or anything, and this is the only implementation that I have for it. So this one single function now works for, this one single function works for every single iterable type, no matter what. Okay. What is unique about this, though? What is the return type of this? It's a weird return type. Okay. So this return type, it's actually, I put it on this previous line. It is enable if is iterable value void. Okay, cool. Any thoughts on what this might do? Okay, yeah? Exactly, right. So this is iterable method right here. So notice that we're passing in this type t. So we're giving it this type. And this type could be a vector, it could be an integer or something. And it's checking, is this type iterable? And if it is iterable, then go and use this return type, which is void. So we're saying if it's iterable, then assume the return type is void. If the object is not iterable, then just delete this function and do not implement this. And therefore, have it fall back on the default template implementation. So that is what this is iterable, an enable if thing is. And so, enable if is this really cool feature that was added, I think, in C++11 or 14. And what it will do is it will enable you to enable certain function implementations depending on what type you're trying to give it. And here we have is iterable. This is actually something that I created. But we could also, we are given things like is an integer or is a float. Or there's a bunch of other basic STD is this qualification about this type thing. And that's meant to be used for enable if. Question? I would say, so there's 10 ways to do everything. This is specifically, I just wanted to show you enable if, which is an old school kind of way of doing this. But there is actually a newer way of doing this, where instead of doing void, we can turn this into something that looks a little bit more familiar. Okay, and instead of just like this code, now we can add an if statement, and we can say if is iterable t value. So we're saying if it's iterable, then use this. Otherwise, go and just print it out. Okay, cool. So now take a look at this. So this should be setting off some red flags as well. So we're saying, so if our value is iterable, then go and iterate through it. Otherwise, go and print out this value. But this is iterable method is actually figured out at compile time. So because of that, only one path will be taken, like no matter what. Like depending on whatever type we pass in. Remember, templates, like this is a function, like this will generate a function for us. So therefore, we know that this if statement right here will actually be deduced at compile time. And if we want, we could be extra explicit about it. We could say if const expression. Okay, so now, ready for this? I'll say iterable. Okay. Do I need to specify C++20 maybe? std equals C++20. Still not happy. Oh, because I still have this up here. That should be fine. Good. Value. It's not value anymore. It is value. That's fine. Okay. Debugging on the fly. There we go. Cool. Okay, so now we have this much more kind of readable print method. Yeah, that is now choosing, like if it's iterable, then it'll take this path. If it's not iterable, then it'll take this path. There we go. And this will still elaborate out to like multiple different functions depending on what we want. But it's basically the exact same thing as this enable if. The reason I'm showing you both is because enable if is still used more commonly. Okay, so coming back to like the first thing that one of the first points that I made in this lecture, why would we potentially want to use this like really old kind of ugly way of writing C++ code versus this kind of more like intuitive like if statement way? Any thoughts? Why not use the newfangled like features all the time? Yeah. Yeah. Exactly, yeah, because G++ could be buggy and will be buggy the more and more advanced and like modern features you use. Yeah, exactly. So therefore, it's like, this looks better, but also like could be kind of dangerous. Okay. The last thing I just wanted to say, I know we're a little bit over, but here is how I implemented is iterable. So take like 10 seconds and just kind of look at this. So notice, so by default, I have this is iterable object with a const expression value set to false. So by default, everything I'm saying, by default, I'm saying nothing is iterable. But then down here, okay, then I have this like monstrosity right here. And what this monstrosity is saying effectively, like if this t object has a .begin method, then go and now set value to true. And I'll talk more about this, I think, on Monday. But that is effectively that is how you implement this. You're saying, like, here's this object, and if this evaluates to true, then we'll go and, like, set this const expression value to true. Yeah. Okay, any final questions on any of this? Okay, yeah, question?
Is the only reason you made the is iterable function instead of just doing that in the code just to make it look more visible?
So the entire reason that I have, right. You're saying, why did I not just like copy this part and put this in the code? Yeah, exactly. Yeah. But yeah, and also the whole point of is iterable here is, so that I don't have to use polymorphism and I don't have to deduce the types at runtime. Instead, like, remember, templates are all figured out at compile time. Yeah, pretty sick. Okay, a couple questions, yeah?
Yeah, thank you. This is simplifying. So what's the difference between auto and template again?
Yeah, template gives you more flexibility. Auto is fewer characters. But template, like anytime you like really need to deal with types, always use template. Anytime you're just like inline, like, oh, let me just like, it'll be faster to just use auto. That's when you use auto. Yeah. Yeah, question?
Yeah, it's about like the syntax of template.
Yeah.
Like, you declare template, type name T multiple times.
Yes.
Is that, like, relegated to like the scope of the function is like above?
That's exactly right. Yeah, so notice that I'm just declaring type name T. That is saying that the thing that comes afterwards now is given this type T. And then once we leave this object, then now type T does no longer exist. So I can't use like T down here. T does not exist anymore because I'm out of this scope. Yeah. Yeah. You're saying like this with enable if versus this if context for, yes, they will be exactly identical. The assembly will be exactly identical for them, assuming that G++ is implemented without bugs. Yeah. Yeah. Question? I guess, so the more that you see this, type of code, the more readable it becomes. Yes, so therefore, I would not say it's necessarily readable versus optimized, although arguably this is more, like this style would be more readable, although it is very optimized. It's readable because it's consistent with other styles of writing C++. But if you're really used to enable if, then this would also be considered readable. Just depends on your background. Yeah. Yeah, but I do agree. This is kind of ugly. Actually, probably everyone would agree that enable if is really ugly. Okay. Thank you, everyone. We will resume on